I'm going to keep telling you guys the truth for historic and history's sake. Is that all you have to say, troll?
So we need to clarify this. Can MOSFETs take a low voltage signal and turn it into AC current, or do you have to supply current from the source in order to get current out? Here's what one of my YouTubers said. Highlighted reply at Colin Waters, 1H ago, 56575. MOSFETs don't really turn a low voltage into AC current. They use a low voltage to control current from a power supply. The AC current comes from the power supply, not the source of the low voltage. So which is it? Does a MOSFET convert voltage into AC current at high switching speeds, or can't it? We need to know if it's possible to make current just like it's possible to make voltage. We can use a generator to make voltage, but is it impossible to make current? Is Nikola Tesla wrong in saying that if you pull something at high speed, you get current? Or is this gentleman right in saying that it's impossible for these devices to make current from voltage?
Even though they were told by professionals that this wasn't true, they keep persisting that this cannot be done. Let's look at that for a minute.
The thing is that this just receives low voltage signal at a very, very super high frequency, okay? Once again, thousands of times per second switching in order to turn DC into AC alternating current. Okay? In order to turn DC into AC alternating current. Okay? In order to turn DC into AC alternating current. Okay?
And this is the reason why we go to AI, to get basic questions. So let's see what AI has to say.
Colin Waters' response is well informed, and he's essentially clarifying that the current spikes you see are real, but the energy for those spikes originates from the gate drive voltage, rather than being created from nothing. His main point is about the terminology. He's cautioning against using the word generated in a way that might be misinterpreted as producing more energy than what was originally supplied. Breaking down his response. 1. He acknowledges that fast voltage pulses to a MOSFET gate do create current pulses at the drain source terminals. This agrees with what you observed in your experiment. 2. But those pulses depend on energy from the input signal, including parasitic capacitance effects. The MOSFET's internal capacitance temporarily stores and releases energy, causing a measurable current pulse. However, he argues that this is not true generation in the sense of creating net new energy. 3. The energy in the output current spikes is less than the energy in the input signal. This means the system is not amplifying power, just redistributing it in a pulsed form. 4. The issue is the word generated. He's saying that people might misunderstand your claim if they think the MOSFET is producing current without an energy source. How to reply back? You can acknowledge his experience while reinforcing what you are actually demonstrating. Reply. I appreciate your insight and agree that the term generated can be misleading in the context of energy conservation. What I am observing is that by switching voltage at high speed, I can produce measurable current pulses even when no significant steady-state current exists. I see that this is due to the MOSFET's internal capacitance and transient switching effects, rather than creating energy from nothing. My real question is, if current pulses can be induced this way, can they be leveraged in a practical system to do useful work, such as charging a capacitor or driving a load efficiently? Tesla's work suggests that high-speed pulsing interacts with electromagnetic fields in ways that could recover energy, and I'm exploring whether there's a way to apply that principle here. What are your thoughts on that? This way you avoid debating the definition of generation, and instead refocus the conversation on a practical engineering question, whether this phenomenon can be harnessed for useful energy transfer. That keeps the discussion constructive while still pushing for new insights.
And also, written in the datasheet should be able to switch up to 200 amperes. I have no idea if you really believe this number from bottom of your heart or not. If you have doubts about this number or you think that these numbers are just lies, I have to say that you are not alone. Many people don't believe it because these numbers are not correct in fact, and the power of the parts like this one is much less than the numbers like 200 amperes. But it's interesting to know that many people, even professionals, don't have accurate information in this regard. In this video I want to talk about it and clear up some ambiguities once and for all, whether a tiny component with relatively thin pins like this IGBT can really switch 200 amperes or not, and if it can, then what is the real power of the components like this one? To start, I think the best thing is to go to the datasheet first to see if it is really written in the datasheet that this IGBT can switch up to 200 amperes, or if the online stores have written something wrong. After all, we consider the datasheet as a reliable source for getting information about parts. This is the datasheet for 30G124 IGBT. If we take a look at page 4, we can see that a table of basic specifications of this part is given here. Since our desired part is in the TO220 SIS package, like this one, we have to look for that part in this column somewhere here. Look, here it is. GT30G124 is mentioned here. If you look carefully, you can see that 430 volts is written here in the breakdown voltage column, which means that this part can switch DC loads up to 430 volts. If you look carefully at the adjacent column here, it is related to the current of the part. Look, yes, 200 is written here and their unit is written here as amperes. So far, what is written on the online stores is correct. Is written here as amperes. So far, what is written on the online stores is correct. Okay, it's correct that 200 amperes is written in the datasheet, but does this mean that we can actually draw 200 amperes from it in reality? Yes, we can, but it has conditions. Usually, when we talk about the current of parts like transistors, we mean how much current we can draw from the part steadily and continuously. But this 200 amperes written in the datasheet does not mean that. If you ask why, I have to show the answer on the datasheet. 200 amperes is written here. Correct. It is written in the current column. This is also correct. But if you look carefully, you can see that the current column here actually has two segments. The first one is related to the continuous current of the part, which mentioned as DC, and the second one is mentioned as pulse, which means the instantaneous current. This 200 amperes is written in the instantaneous current segment. So far, it has been determined that this part can switch up to 200 amperes of current, but only for a very short moment, right? If you want to draw 200 amperes from this part for a longer period, even for a few seconds, for example, it will definitely be damaged or even explode. Here, you might wonder how much my short moment means. That is, how long is this 200 ampere tolerable for this part? To find the answer to this question, we have to refer to the datasheet again and review it carefully to see if there is anything written in the datasheet about the current pulse duration or not. I looked for the pulse duration parameter in the datasheet and finally found it. Here on the page 12. Here on page 12, there are several tables that write the power of the parts. For example, look, for GT30F131, it gives 140 watts, and for GT30G124, it gives 25 watts. I don't care about the power of the parts for now. What is important to me is the number written here. Look. Here again, 200 amperes is written, but if you look carefully at the top, it says ICP at 3 microseconds. I believe the factory determines here what it means by a 200 amperes pulse. That is, if we want to draw 200 amperes of current from this part, we can only do this for 3 microseconds, and more than 3 microseconds will damage the part. When we talk about the current of parts like transistors or IGBTs, we usually don't mean a 3 microsecond pulse, right? In fact, we mean the other column, where a smaller number is written which is related to the continuous current of the part. As far as I remember, nothing was written there for this guy. That's right. For this part number, the amount of current that it can switch continuously is not written here. Probably the amount of steady state current for these part numbers listed here depends on many conditions and parameters, so they couldn't write a specific number here. Let's make an estimate ourselves. Although this is not very principled and reliable, but if you look carefully, you can see that for other parts, it can be said that the continuous current was almost half of the instantaneous current. For example, here it was 20 amperes, it became 10 amperes. Or here it was 120 amperes, it became 60 amperes. Of course, there are exceptions. For example, here was 100 amperes for instantaneous current, it became 30 amperes. Now, if we want to make an estimate, I say that for 30G124, if we consider the same coefficient, we should say that it can probably switch about 100 amperes continuously. I said before, I emphasize again that the calculation we did and divided 200 amperes by 2 and got the number 100 amperes is not principled. But let's assume that this number 100 amperes is correct. It is true that we didn't accept 200 amperes and reach the number 100 amperes, which is much less than 200 amperes. But this number 100 ampere itself is still very high, and it is not the number we were looking for. So I think there must be something in between. Let's review the datasheet together again to see if another point can be found or not. If we look
Yes, when you move beyond standard MOSFETs into high-power switching, the names and technology change. Here's the breakdown. 1. Standard MOSFETs, small MOSFETs, used in microelectronics handling milliamps to a few amps. Power MOSFETs, used in motor control, inverters, and power supplies, typically switching tens to hundreds of amps. 2. Super high power MOSFETs. Heatsink mounted power MOSFETs can handle 200 amps to 1000 amps, but usually with very low duty cycles, microseconds or milliseconds. Example, IXIS-IXFFN 420N20T, which can handle 420A at 200 volts. And 3, when MOSFETs are not enough, when you need even higher power, MOSFETs become inefficient due to high on resistance and excessive heat. That's where IGBT's insulated gate bipolar transistors take over. 4, industrial scale high power switching, IGBTs, insulated gate bipolar transistors. IGBTs combine the voltage control of MOSFETs with the high current capability of BJTs. These can switch hundreds to thousands of amps at kilovolt level voltages. Example, Infineon FF1200 R7IP5, which handles 1200A at 1700 volts. Used in EV motor controllers, industrial inverters, high power SMPS, and rail transport systems. Thyristors, GTOs, IGCTs. When IGBTs aren't enough, industries use thyristors, gate turn-off thyristors, GTOs, or integrated gate commutated thyristors, IGCTs. Can switch several thousand amps at multiple kilovolts, used in power grids, industrial motor drives, and HVDC transmission. Example, ABB5STP 20T7H2800, 2800 volts, 2700A. How big are these? Power MOSFETs can fit in TO247 or TO264 packages a bit larger than a coin. High-power IGBTs are often brick-sized modules, 6-inch square or more. Industrial thyristors are as large as a dinner plate and require water cooling. Hair summary, device type, max amps, max voltage, size, usage. Small MOSFET, 10A tie, 100 volts, tiny SOT23s. Microelectronics, power MOSFET, 2500A, short pulses, 20,000 volts. TO247 to brick-sized inverters, motor controllers, IGBT 2000 AM going at 3000 volts, palm size to large bricks, industrial power, EVs, trains, thyristor, GTO, 5000A plus, 10 Kelvin plus large plate-sized, power grids, industrial motors. If you're looking for giant MOSFETs, the closest equivalents are IGBTs or power modules, multi-die MOSFET assemblies in one package. Would you like recommendations for specific applications?
The device Nikola Tesla designed that can handle transit energy. It's time to stop talking about this and you guys start doing it. We showed the examples. We giving you illustration of other people doing it. We show you patterns. What the MOSFET does is exactly what we've been telling you. They can take voltage and transfer it into amps. Believe it or not, we're moving into the future. Thank you.